Thanks, everyone. This is paper session number 5, Methodological Advances. I'm Matt Williams, RTI International, and I'll be just keeping track of time and trying to make as much time available for our speakers as we can. So we're shooting for 12 minutes each, and I'll give you a heads up at about 10 minutes. And I'm hoping that we should have plenty of time for questions and answers. So without further ado, let me turn it over to our first speaker, Tucker.
Okay, I'm trying to share my screen. Let's see. There we go. Okay, so thanks for the invitation to come here and give this presentation. This paper is a little bit more methodological than some other of the talks. So my title is Analysis of Crisis Effects via Maximum Entropy. I'm developing some tools for analysis of time series subject to extreme effects such as level shifts and temporary changes and such. My goal is just to give kind of that methodology in very broad strokes without getting into any of the nitty-gritty, and then sketch out through an example the kinds of analyses that can be done. So here's a standard disclaimer from my work. Okay, so here's the overview. So crises such as the COVID-19 epidemic, but you can think of other things such as the Great Recession. These can have a huge impact on economic time series. They distort historical trend patterns and potentially also seasonal patterns. The extremes can not just be isolated outliers, but can be clustered, and that's quite common. So our goal here is to identify, estimate, and remove those extremes so that you can do other kinds of analyses that are predicated on having a fairly regular time series sample. For example, seasonal adjustment. That's one of the things that, one of the topics that I work on quite a bit at the Census Bureau. So in this paper, I propose this, or really extend a maximum entropy framework and generalize. So I had previous work where I focused on just simple additive outliers. So here it's being extended to more general types of extremes, including level shifts, temporary changes, and seasonal outliers. So specifically, the project shows how to compute the likelihood function in the presence of these specified extremes. The time series process can be non-stationary. We like to use ARIMA models in time series, so those are fine. You may have missing values and you may have extremes present. So given the fitted model, the paper discusses this extreme value adjustment, which is based off of linear projections. So those just involve calculations that require covariances. There's also a test statistic, allows you to compare two different specifications of extremes so you can decide which one may be more appropriate. There's a method for removing those extremes, that's the extreme value adjustment, and that can also be modified to a shrinkage method where they're sort of partially removed. And then you can do filtering afterwards. Sometimes you want to add extreme values back in after you've done the filtering. I'll explain that very briefly. And then there's an uncertainty quantification for all of these procedures. So briefly, this max entropy framework is kind of a fancy name, but the idea is you want to find a linear transformation of the data that removes extreme effects entirely, leaving regular values, or the idea is that the time series sample is made to look more like a Gaussian time series. So Gaussian random variables have higher entropy than other kinds of distributions, given their mean and variance. So it's in that sense that you're maximizing the entropy. These extreme effects typically are modeled as impulse regressors with fixed coefficients. That's sort of common approach that's been around since the 70s. Here, the novelty is using stochastic coefficients instead. It changes the statistics a little bit, and you end up kind of working with covariances rather than the mean function in terms of your estimators. And the third point is just talking about if you have two or more sets of extremes, you can compare two at a time as long as they're nested. So there's a chi-squared statistic, kind of like a walled statistic for making those comparisons. So the extreme value adjustment itself, these are defined by a linear projection. So formulas just involving covariances onto the regular values. So those are the values of the time series that don't have extremes. And it's a little bit subtle, but all the math is basically linear algebra in the end. So another thing that I wanted to add into this project was imputing missing values, especially if you have you want to do forecasting or backcast extension of the time series. It's convenient to sort of place missing values on the beginning and ends of the sample. So the method also handles that. Basically, there's a decomposition of the time series additively into different components. You have the extreme values, and then the rest of the series, the regular values, and then you can filter the extreme valued adjusted series. So I'll just try to show the main idea through this illustration. So this data set was kind of interesting, came to our attention in 2020, National Unemployment Insurance weekly claims. And they just, the claims surged to these unseen levels in the opening of the pandemic, March 21st, 2020. So I'll show that in the next slide. And then I'll also show how one can specify extremes such as additive outliers and level shifts. And I've made a choice of 3 level shifts and 9 additive outliers. There's other choices one can make, of course, but this one did give a good fitted model. And then finally, I'll show the extreme value adjustment and a seasonal adjustment application. So this is the data actually in log scale, because if I didn't log it first, the spikes are so, the spike at the pandemic era is so huge that you wouldn't really even be able to see the seasonality and the other movements happening in pre-pandemic years. So that's why I present it in log scale. But the basic behavior here, there's a seasonal pattern. There's some maybe cyclical movement over the decades, and but most importantly, there's this huge upward spike. So applying a basic seasonal adjustment filters to that raw data without adjusting for the extremes is a bad idea. It'll generate a lot of problems with the adjustment. So what we want to do is identify these extremes, sort of chop them out, remove them using this extreme value adjustment procedure. Then we'll filter the resulting regularized time series, and then we'll add back any extreme value effects that are pertinent to that. Actually, I'll get to this. The seasonal adjustment should have additive outliers and level shifts because those pertain to non-seasonal effects. In any event, so focusing on 2019 forward to present, and again in log scale, here we have the data. And the extremes that I've identified through some exploratory analysis, it's a bit of trial and error at this point because I don't have an automatic identification scheme. But for any outliers that are identified, you can compare those different specifications. So through a bit of experimentation, I came to the 3 level shifts marked in green. These seem to work well. This first upward blip is actually 2 data points. So it jumps up to the green dot, and then it jumps up further to where the red dots are. So the upward movement's not just in 1 week, but in 2 weeks. So with that specification, am able to fit a model. The residuals, time series residuals, don't have any serial correlation, so I'm happy with the model fit. And I get this extreme value adjustment. This is showing the blue line here is extreme value adjustment. So it's removed this big up spike, and it's also showing kind of a downward movement of the claims once you've accounted for those level shifts. The shading there is the uncertainty. So that's plus or minus 2 square root of the mean squared error for the extreme value projection. And then there's also a 10, I guess I go 20 steps back and 20 steps forward.
2 minutes.
Yeah. So there's a bit of shading there. The trumpet shape is just showing that the uncertainty increases the further away you get from the sample. There's uncertainty in the middle here because that's associated with the extremes that you're adjusting for. There's a shrinkage version too, but I'm not displaying that. So that can be filtered, and then you add those extremes back in afterwards. As I mentioned, those are non-seasonal effects, so they belong with the seasonally adjusted component. In blue is a seasonal adjustment. It tracks this original series in black very closely, so you don't see a big discrepancy. I'm actually happy with that result. But you can check, and I did check, that the seasonality has been removed. There's actually uncertainty bands on this too, but they are very tight, so they're not clearly visible. Yeah, so I'll just wrap up. So this is the quick view of this maximum entropy methodology. Allows fitting, testing, extreme specifications, adjustment, filtering, and I have stuff on this GitHub repo. Great, thanks for your attention.
Thanks, Tucker. As we transition to our next speaker, it looks like you've got a question in the Q&A. In the UI data, why does the x-axis of the y-scale show negative values?
The x-axis.
Why does the y-axis of the y-scale show negative values? I'm sorry.
Oh, the y-axis. Yeah, well, it's logged.
Thanks.
Yeah. The original data, of course, is all positive, but you can have values that are less than 1. So once those get logged, they can you can get negative values.
Great. Thank you. Andrew, are you able to share your screen? All right, thank you. Take it away, Andrew.
Yes, sharing my screen, no problem. Getting off mute, a whole nother story some days. Well, good afternoon, everyone. My name is Andrew Dow. I'm from the USDA, United States Department of Agriculture's National Agricultural Statistics Service. Today, I'm going to talk to you guys a little bit about our process to develop a parameterized and enterprise-ready survey data review tool. I would like to acknowledge my co-authors on this, Michael Jacobson, Ryan Morton, Jared Pratt, and Justin Van Wart. As you've seen throughout the process here's our disclaimer. These thoughts that you're going to hear are mostly mine and not necessarily that of the USDA or the US government. So some background on what NAS is, what NAS does. USDA NAS, we collect over 400 different surveys annually. And I say 400 surveys when I'm talking about survey instances. So if it's a monthly survey, I'm counting that as 12 in this count. Every 5 years, we conduct our census of agriculture, and we have a lot of data coming in, from surveys. So we need to spend some time reviewing that survey data, really looking for elements of survey error. And in particular, today, I'm going to focus on some ways that we kind of look at the data after it comes in, and we start to get some understanding of some sampling error, some measurement error, and also some processing error, which can creep up as you're working with this survey data. So our motivation, we have a legacy tool right now that we use to look at these surveys, and it was developed in SAS AF, which for those of you who are familiar with it, has been around for a long time, but is no longer enhanced by SAS. It hasn't been since the early 2000s, I think, at this point. The legacy tool was also it had morphed over time. The first one went on board in 1994, and it morphed into 26 independent systems. Lastly, our motivation is we're in the midst of an Azure cloud migration right now. And so we're looking at things that are easily portable to the cloud. Those SaaS AF applications were not necessarily that. So where do you start when you're dealing with a process like this? Well, right or wrong, we kind of actually started with technology. And there were multiple solutions that could be used. So we actually conducted a big technology bake-off. We had some contractors do stuff. We had some internal folks do stuff. We looked at HTML5, just straight up applications. We looked at JavaScript stuff. We looked at Tableau. We looked at Power BI. And then lastly, we looked at R Shiny. After an evaluation process, we elected to go with R Shiny. So the tool I'm going to show you a little bit later in some slides was developed using R Shiny for a few reasons. One is we could lead the development process internally. And a lot of times when we do projects like this, the translation of our business logic into usable and serviceable applications can be a little bit difficult. So this kind of got us around that. Also, it allowed people like myself who are not full stack web developers to kind of pretend to be one for at least a little bit of time. I could build and deploy applications that meet the needs of our business users. So I'm going to come back to this timeline quite a bit as I go through this talk. Because I think it's important to understand how these pieces all fit together. So we started with that technology bake-off, and we decided to go with R Shiny. At the same time, we had a new survey coming on board at NAS, one that did not previously have one of those analysis tools that I talked about. And so it was a great opportunity for us to kind of test some things out. So we ended up building a prototype application for that survey that came on board. And it worked okay. It allowed our staff to adequately review the data, and it had the charts and plots and maps and tables that they needed. For a user, it probably actually looked quite professional. However, from my developer standpoint, I knew the code base had some downfalls. It wasn't very pretty. We weren't leveraging version controlling at that point in time. It became pretty obvious that we needed some help. So we actually did some searching around, and we found there are people out there who are professional Shiny developers. And we ended up pulling one of them on board and actually embedding them within our team. So oftentimes, a lot of these types of projects end up going to a full contracting group. In this situation, we actually focused on one individual and embedded him within the team, and it's worked really well. He's enhanced and helped with design, of course, some of the architecture of it, but also instruction. He's taught our team a lot of how to actually develop these applications and maintain them, and kind of brought some industry standard, practices and best practices to light amongst our team. So once we had our contractor embedded on the team, the process began to start building our generalized application that would handle all 400 of those surveys. And so you'll notice here, we're making a switch from 26 independent applications to one application, which will hopefully serve everything. Our goals were to make it as minimal maintenance as possible. We wanted everything in there to be parameterized. In theory, when we get to the long end goal here, we don't want to be looking at the code base every single day. Instead, we'd like to be able to control what the application does by a series of parameters. And we've had very good luck with that. They control everything from the variables you see to the types of analysis you're using to the types of imputation and reweighting you're using. All of that controlled through a series of parameters that our developers within our division can actually go in there and add and set up the tool for our end users who are interacting with it. So at this point, things were starting to come together as we kind of worked out and got close to this version 1.0 application. However, despite our best efforts, we probably overlooked some stuff as we started working on it and developing it. So at this point, we formed a really, really large group, 47 users that we divided into focus groups. We had some doing surveys, we had some doing load testing, we had some testing specific screens. We basically created a giant feedback loop that really helped refine the tool and answer a lot of questions. We sometimes had split votes on things like that. And this was a great way for us to actually get some opinions from folks that would actually be using it. So this is something I encourage, if you build any of these applications, make sure you bring that end user along as you possibly can from the beginning. So we got our feedback loops in the mix now. Now we're getting to the point of, all right, we want to finalize these applications. We want to do some parallel testing. We want to actually get this into production. And there's where all of these things and a lot of these topics have come up over the last day or two, I've noticed from folks. On ways to make things portable, ways to make things set up for the cloud environment. So our application is actually it's an R package that we've put together. Everything is containerized with Docker. All of our version controlling is through Git. And we've recently added some continuous integration and continuous deployment structure through GitHub Actions, which allows us to basically commit code, and it will go all the way through the process of creating our container, pushing it to a repository, and then ultimately deploying it on our app server. So that's been very smooth and a pretty successful route for us so far. So that's where we're at. We actually have about, I think, a dozen of our surveys right now currently using it in a production setting, which of that 400 would probably account for about 30 or 35 of them. By the end of the year, we're hoping to be well over 250 of those. And by the middle of next year, I'd like to have absolutely everything of those 400 surveys using the new system migrated from their legacy applications. So we've got about 5 minutes left here, and I'm going to take some time to kind of show the tool off itself. So we have named the tool. That's always an important thing. Anytime you build an application, is coming up with a name, and we're the government, so we like to use acronyms. And so we called it IDART, which is the Interactive Data Analysis Review Tool. The page you're seeing here is our main landing page. Developed here in R Shiny. We've of course added some custom CSS because you don't get some of this type of stuff out of the box with Shiny, but you have a lot of flexibility in what you can do. The tool itself doesn't require like any data setup per se. Those parameters control what data you're looking at, and behind the scenes, we have a separate R Plumber API, which is constantly going and getting data from the database and formatting it in a form that our application wants to work with. Believe it or not, the way the data is structured in the database is not exactly how our application wants it. So we added that API layer to help solve some of that. It also helps us merge different data sources together when we have maybe some external data that goes along with this survey data. It's provided us with a lot of flexibility as we've been working through this. One page that our users spend a lot of time on is this analysis page. This is kind of if you wanted to go through variable by variable on a survey. You'll notice I blacked out some stuff. This is actually all mocked up data, but just to be like overly cautious, I end up blacking stuff out as well. So nonetheless, what you can see here is one of our analysis screens where we have a scatter plot. I think of ultimately stuff like this will probably turn into box plots, but we have some institutional knowledge and some institutional usage that involves scatter plots. And so this is what people are comfortable with. Over time, I would expect stuff like this to probably morph a little bit, but we have flexibility. Everything here is modularized. Making a change like that to change it to a box plot would actually be pretty straightforward for us. Everything, of course, also is in a table view. The reason I bring this up is I want to just remind folks that tables are data visualizations themselves, and you got to keep that in mind as you work through stuff. So formatting of tables, how those tables interact, what actions perform when you click on rows, they're all very important, especially in these interactive web applications. We have the ability to compare data. This is also useful for us. So we don't do a lot of panel surveys at NAS, but we do have people who end up in our surveys quite often. And this is one of our mechanisms. We are able to compare their data that they report now versus what they've reported previously. This is our record screen. So as you drill through the tool, sometimes you want to narrow it down to just that one operation you're looking at, that one outlier. You have that ability here. We have some mapping in here as well that I've kind of hidden at this point. We also have some weather data that might be appropriate because we're looking at agricultural data here, and weather can have a drastic impact on that. We have some indications. So these are your kind of direct expansions and totaled estimates for the survey. But here's the one I want to spend the last minute or two here on, because I believe that's what I have, about a minute and a half.
2 minutes.
Cool. Thanks, Matt. I knew it was coming. The thing I want to focus on here is this anomaly detection screen. Lucas Artur gave a talk yesterday, so hopefully a lot of you were able to attend that, where he kind of talked about some of our mechanism and our algorithm for understanding this. Yes, it's really useful to sometimes click through a bunch of variables and go through this process somewhat manually, interacting with the data. But there are also surveys we have that are quite large. We have data coming in constantly. We might get 50 reports in the last hour, and you got to figure out, do I want to go through all those? How do I go through it? So we've incorporated some machine learning approaches here that identify anomalies. And we're looking at things that are impactful, things that are outliers, things that are relational anomalies. So that would be like a high corn yield and a low soybean yield might be a relational anomaly that we would pull out. And then historic anomalies. And so this screen is really designed to try to identify that and take some of the manual processes out of it for our field offices that are reviewing this data and make it an automated approach to anomaly detection. in particular, and Luca probably talked about this a little bit yesterday. I wasn't able to make his talk on it, but this came from an in-house data science competition we had, where we actually ran one. We had 6 different entries. Theirs ended up being the one that was submitted that won the contest. We had some pretty good rubric that defined what was usable or not, but that came from it. Our last thing I want to talk about here is actually our ad hoc screen. Despite our best efforts, we didn't get it all. There's a few things that needed to be, explored by users themselves. So the ad hoc screen is a way for them to go and choose the variables they want, make calculations, make filters, and we've got everything so you can save it, and we can ultimately determine later on if this is something we want to incorporate within the application itself, just to make it a standard view for folks. In conclusion, the 4 things I want to focus on here is make sure you spend time understanding the task. We did not jump right into this. We spent a lot of time understanding what the needs were for the users. Bring the user along for the ride. Don't rush. Take the time to do it right. This project has taken a little bit longer than I think folks had hoped for. That's okay. We're really taking some time to make sure we do it right. And then lastly, find some help if you need it. If you get stuck on something, I have a rule within my team. If you spend more than 15 minutes looking at it, put it out to the whole team, because somebody's probably run into it before and has already solved it. So I went over just a teensy bit there, Matt, but I will turn it back over to you at this point.
Thanks, Andrew. You've got a Q&A in if I've got a question for you in the Q&A, you can kind of take it up offline or at the end of the session. Let's transition now to our next speaker, Michelle.
Let me just share. Hi, everyone. Can you see my slides?
Yes, can you do full screen for us?
Okay, does that look okay?
That's presenter view, so we can see your presenter.
I got this. I don't know.
No problem. You know what? I think you can go ahead. It's fine.
The
Thanks.
little book mode is also good.
The book mode. Display settings. Does that work?
Oh, that's
Yes.
perfect.
Okay,
Thank you.
sorry, I had multiple. Okay. So my name's Michelle Mellers. I am a research associate at Uniformed Services University of the Health Sciences, and I'm presenting today on a computational pipeline applied to a nested case control study simulation that we're working on here at USIS. Here's the disclaimer. Basically, the views are my own and not the views of the DoD. So some of the motivation for this is really trying to understand how to follow the FAIR principles and creating a reproducible pipeline within this nested case control study. The FAIR definition, just as kind of a review, is findability. All data must be findable with a unique identifier. data stored in a searchable resource, accessibility, machine and human readable, reside in a repository, interoperability, data shares a common structure, metadata recognized, formal terminologies are included in the description, reusability, clear storage licenses, and must meet relevant community standards. And pipeline, a little bit of a review. They describe the flow of data processing and analytic steps for a project. And it really helps to organize all the required computational tools and linking all the discrete steps together within the pipeline, and really ensures that we're following the FAIR principles as we're implementing the analytic parts of studies. And pipelines really allow you to follow the FAIR principles by following findability, where you have a meaningful description of the data, accessibility, provides clear guidelines and requirements to obtain the data use, interoperability, standardization of software tools, reusability, a clear structure of the pipeline, inclusive of test files, use of version control, even just setting up automatic version control. But what does this really mean when we're applying it to a pipeline, when we're setting up a study for a nested case control? And we're creating simulations of varying complexities to improve the understanding of the data structure, the analytic plan, and the potential interpretations for this study. So we're really building it up, and the pipeline and everything is built before we're even seeing the data. It really allows us to raise questions about what sort of analytic tools and really work with the subject matter experts. So questions are answered before we're really seeing the data, or at least as best we can. And we're really testing the pipeline and performing all of what using simulations and performing all of as much as we can in preparation before we see the real analysis. Again, there are lots of different tools you can use. Lots of different people have their different favorites, DocStore, Apache, SnakeMate. You can even set up pipelines. It takes a little bit more work using a bash script or interactive notebooks, just really something that can formalize what you're trying to do. So let's go to our example. And this is part of a nested case control study. And we were starting it just using R Markdown, and it's a Monte Carlo simulation. And that is allowing us to set up our pipeline. And this is a study that is examining the effect of chemical exposures on breast cancer risk. And the simulated data set that we came up with is breast cancer status, chemical exposure values, related demographic information. And just so you guys get a little bit of what sort of idea of what sort of data we're going to see, a lot of this data is going to be in what's called dose response curves. And I have the 4 that are very commonly seen across the bottom: linear, polynomial, exponential, and change point. And what's going to be really important about these curves is not only the curves themselves, but what's going on in the nonlinear space of these curves to help identify some of the scientific questions. So we're using the second derivative just to give us a basic measure and understanding of the curvature. There's a lot going on with these curves sometimes, and it just makes it easy to see. So on the left, you have the dose response curve, and on the right, you have the second derivative. So this is basically just a flow diagram. It's lets you just kind of organize your thoughts and go through the steps. You start with your scientific question or hypothesis and really hammer that out. Requirements are always, I think, one of the hardest parts. I know it's a whole specialty within software engineering, is generation of requirements. really making sure you understand what needs to be done. And then we move on to really organizing the pipeline structure, right? And then we just go to writing code for the statistical files, visualization files, reviewing the code, making sure everything's there. And you can go around, obviously, with the review. Sometimes you have to replan based on what you're seeing in the results. Once you go through review, you write organization files so it's easy to run. And then you have your final outputs. So again, what is the application? Going back to our nested case control study. On the left, you can see we have our simulated data with the chemical BMI. We have covariates, sex, race, age. These are just common things we're expecting to see within the data set once we get it for this study. And then we have the outcomes, which is the linear and nonlinear outcomes. And we have two big initial analysis points that we're going to have to identify, which is identification of the missing data technique, complete case substitution, or nested multiple imputation. And the last, we also want to have some sort of test in linearity in the dose response curve, as that will really inform what sort of techniques we will use in the analysis. So what's the first part of our simulation with our pipeline was comparing nested multiple imputation, substitution, and complete case. This type of data has two different types of missing. We'll have chemical data missing, which is left censored, which means everything below limit of detection. At this case, you can kind of see it around the value of 0 will be missing. And you will oftentimes have covariates where it's missing across the range of values. And which means since you have two different distributions, something like mice sometimes can be tricky to implement, which is why we were testing a new tool a technique called nested multiple imputation. And we examined obviously the fit and functionality of these tools through the assessment of the fit of the curve. We did find that the bias is greatest through below the limit of detection. And you can see that the bias is different across based on the shape of the curve that we're going to see. The bottom is the change point models, and you can really see how the bias, again, really that is different based on where the change point is placed in the curve. But one of the main things we did find was that mice in R was incomplete in the implementation of nested multiple imputation. So we ended up having to do some software development to fully implement nested multiple imputation within R. And by already having this pipeline set up, we were able to come up with scenarios and test it for accuracy using this simulation. So the last part of this was really trying to understand, or the next part of this was, okay, we have these curves, are they linear? We're going to have a lot of different curves coming in, so we're going to have some sort of test where we can rapidly test lots of different curves for linearity. We compared two different methods. Equation 1, you have the smoother, where it's just a smoother or spline. Equation 2, you have where you have two separate values. You have your beta 1 and your chemical value, and then you have your second derivative.
About 2 minutes.
Oh, thank you. And we compared these two. Obviously, they did what we wanted statistically, but more importantly, we were able to take this simulation to the scientist and subject matter expert and really start to visualize, okay, how do we make decisions on parameterizing this problem? And we ended up and just using this approach, we could test based on different scenarios. We could test different scenarios based on the thoughts of the PI. And we ended up using the smoother based on, or equation 1 based on the subject matter expert. So what's the next steps? You can always speed up the simulation. It takes a long time to run, course timing, parallelizing, editing the output, and making sure your output files. What are the benefits of formalizing the pipeline? We used a building block approach to really add functionality, and this allows for testing and development of new software as you needed for a project. Like some software was needed to be developed for this project. And again, going back to the FAIR initiative, it effectively describes the data by formalizing the process so the data is findable. Aids in allowing other individuals access to the project. It outlines the software used in the analytic process to improve interoperability, and it organizes the data flow for tracking of each step, which ensures reusability. Thank you, and here's my contact information.
Thanks, Michelle. And as we transition to our next speaker, just a reminder for folks to use the Q&A feature. If you have questions, we can monitor that and direct it to our speakers. So our next presenter will be Sixia Chen. Can you share your screen?
Sure. It says, yeah, I guess. Can you see my screen now?
Yes.
Okay, great. All right,
looks good.
so we'll start. Good afternoon, everyone. Thank you for inviting me to present in this conference. And today I'm going to present some of my recent research work on deep neural network-based mass imputation for data integration. So this is a joint work with my colleague here and OU HSC. By the way, I'm an associate professor in biostatistics at the University of Oklahoma Health Sciences Center. And this is an acknowledgement for the grant supporting this research. And this is outline for today's presentation. First, I will just briefly mention about some pros and cons for the probability and the non-probability samples. Many of you already know this. Probability sample has been used as a gold standard for conducting surveys due to small selection bias and the representativeness. But non-probability sample has some advantages in terms of cost and time. And in a scenario where we don't have any sampling frame available, non-probability sample sometimes can open some room for us to do the research. So next, I want to present some example for non-probability sample. So this is the example that I worked on here. So this is a 2019 tribal birthrates survey that we have done here. The target population of interest is American Indian adults who lived in Oklahoma, Kansas, and Texas. And because we don't have a sampling frame available for us to draw the sample, so we used the non-probability sample by a hybrid sampling design by joining the sample from tribal event. So we send interviewers to the different tribal events to connect data. We also have some email list from the previous surveys. So we send emails to some Native American adults. We also contracted with some commercial company to do a social media sampling so we can target Native American adults through Facebook, Instagram, and some other social media platforms. So as a result, our sample size improved from about 300 in 2015 to about 800 in 2019. So as we can see, non-probability sampling design really helps boost the sample size a lot. So here are some motivations for conducting the non-probability sampling. As we know, that costs have been increasing for all types of surveys recently, and the response rates have been dropping, particularly for telephone surveys and other surveys. And because I work in the health sciences center, so often the time we don't have a sampling frame available. For instance, if we want to study some real disease population like HIV, cancer, because there's no available frame, so we cannot draw the probability sample, so we need to draw non-probability sample. And we also have rich information from the non-probability sample, such as online non-probability panels. So currently, there are many strategies for handling the non-probability sample, including the following methods: calibration method, inverse propensity score weighting method, mass imputation methods, and some other methods. So in this presentation, I will just focus on mass imputation method. So next, I will talk about our proposed method. So our research objectives is that we want to propose a new deep neural network-based mass imputation method for statistical inference. And we want to compare the new method with some existing machine learning methods through Monte Carlo simulation study and real data application. So next, I want to introduce some mathematical notations. So we denote the finite population as Fn. So it has x and y. X is some covariate vector and y is a study variable of interest. And we assume there's a superpopulation model, y depends on some model of x, but this model is unknown. And then we assume there's a probability sample, SA, is selected from this finite population with some sampling design, probability sampling design. And in addition, we assume the non-probability sample S of B is selected from finite population with unknown selection probability. And we assume this probability only depends on X. And according to the reapplication, so we assume that we only observe X in probability sample, and we observe both X and Y in non-probability sample. And our parameter of interest is the population mean of Y. So following the theoretical framework of previous literatures, we define the model structure for the deep neural network. Specifically, we assume that in the first hidden layer, Hj, it depends on X, the input features through this function. So we first do a linear transformation of the input features X, then there's an activation function sigma on top of that. So that will give us the first layer nodes. And those alphas, they are unknown parameters to be estimated. And D is the number of nodes. Sigma is the activation function. Some commonly used activation functions, including the following cases. And in our project, we only considered ReLU activation function because it has computational stability and also theoretical properties. So we define the other layers accordingly. So it's basically a similar linear transformation first, then we use the activation function. On top of the linear transformation, we can define the nodes for different layers. And then for the model identification purpose, we put these constraints. So all the square of the sums, this summation equals to 1. And then, lastly, we have this mass imputation model can be defined as the following. So it's a linear function of the nodes from the final layer. So our proposed method is motivated from the previous literature. And this literature consider imputation method by using deep neural network. So we extend their work by doing the data integration. So the idea is that we can first minimize this loss function by using a standard algorithm, like add-on algorithm. We can estimate alpha and beta. Then we refit, basically we refit a model is a linear regression model by using the final layer nodes to estimate the beta hat. Then after that, we can have this imputed value from the probability sample. Then we can construct final mass imputed estimator. So the good thing for doing this is that we can establish the symptotic normality and the symptotic variance, so we can conduct statistical inference. So I removed all the theoretical results here because we don't have much time to present. But if you're interested, I will be happy to send you the paper. So next, I will present some Monte Carlo simulation results. So for this simulation, we generated 1,000 Monte Carlo samples from 5 populations with population size 10,000. We want to estimate population mean of Y. Specifically, we consider 3 different models. The first model is a linear regression model. So Y depend on 4 different X variables. And the second model is a nonlinear model. So Y depend on those 4 different predictors, but we did some nonlinear transformations here. And the third model is more complicated. It's a hierarchical model. So this is more consistent with the structure of deep neural networks. So we have 3 different layers. We have those nonlinear transformations. All right. So then we select a probability sample with sample size 1,000 from the simple random sampling without replacement. And for models 1 and 2, we do a non-probability sample with sample size around 1,000 from this logistic regression model. So for model 3, we draw a non-probability sample from logistic regression model, but this model depends on the nodes on the second layer.
2 minutes.
So it's kind of a nonlinear transformation. All right, so then we compare different machine learning methods. Those methods right here. And these are the tuning parameters we considered: learning rates, number of layers, and number of nodes. And this is the final results, Monte Carlo results for the point estimation. So as you can see that on the model 1, linear model has the best performance, which makes sense because the model 1 is linear regression model. And the generalized additive model has good results as well. And deep neural network methods have slightly worse results, but it's not too bad because those are percentages, so it's not too bad. It's better than other machine learning methods like XGB, regression tree, and KN. And on the model 2, so deep neural network methods perform better than other methods. And our proposed new deep learning methods have a comparable performance compared to the original deep learning methods. On the model 3, you can see deep learning methods outperform other methods as well. In addition to that, we calculate the coverage rate, 95% coverage rate, based on the confidence interval that we provided. So we have a very good and reasonable coverage rate based on our methods. So here are some discussions. So we also did some real data analysis, and it shows our proposed methods also outperform other methods in terms of the bias. So it can be a very good method to use in practice. All right, so that's all for my presentation. Thank you for your time.
Thank you so much. Just a reminder, please add your questions to the Q&A feature as we transition to our last speaker. We should have plenty of time for question and answers at the end of the session. So Jianru, see if you can share your screen. Looks good. Thank you.
Can you hear me now?
Yes, we can hear you. Thank you.
Okay. Oh, good. So my name is Jianru Chen, currently working as a statistician at Westet. Today, I will introduce an upcoming R package called West Weight as a new R tool for survey weight adjustments. The West Weight package is developed and maintained by WestEd, and I want to acknowledge the contribution of my colleagues, Benjamin and Misa, and they're also the main contributors and maintainers of this package. So let's start with why use weighting. Survey weighting is an essential step in survey analysis to ensure that the collected data accurately represents the target population under the complex survey design to achieve the population representativeness. Certain groups may be underrepresented or overrepresented during the sampling process, so assigning appropriate weights to each respondent helps mitigate the unit non-response bias and to ensure that the estimates appropriately reflect the population parameters. And here are some general weighting steps. After the creation of the weights and replicate weights, the weight adjustment is needed for the unit non-response, where we inflate weights for the targeted observed cases. Then the adjusted weights need to be calibrated to the population control totals to reduce variance and adjust for any coverage error. When the calibration lead to some extreme weights, trimming could be conducted to reduce extreme weights to a certain cutoff. The non-response weighting adjustment could be pursued by two methods. One is the propensity score adjustment approach. The other one is the weighting class ratio approach. I will attach the reference this reference in the reference slide. Calibration using auxiliary control totals could be pursued by post-stratification, raking, and generalized regression estimation. Currently, there are some comprehensive open source R packages for the survey data analysis. I listed some examples here for you to check with a hyperlink, and also some SAS procedures and proprietary macros. And actually, some main functions in our West Weight package are mirroring the regarding WestEd developed SAS macros. So why we want to initiate this R tool development? Our researchers in WestEd have already developed a set of comprehensive tools in SAS for survey weighting to use in a variety of survey projects. But there is the trending clients need for reproducibility and standardization using open source tool. So we decided to develop this open source R package with transparent and documented procedures, which could be easily shared and replicated by the clients. In addition to that, based on the current R tools for using the survey data, we also want to build more R functionalities for a comprehensive validation process that has been developed for decades, which provides tools for dealing with some challenges of using the survey weights in recent days. And I will highlight it in later slides. These R tool would have other benefits too. For example, faster performance compared to our existing SAS macros, especially when dealing with the large scale survey data. The functions, it also has the functions that are designed to be more customizable and user-friendly. And our researchers could contribute to this R open source community and share their expertise in a kind of collaborative environment. So here are some challenges that we should consider when doing the weighting adjustment. As we all know, non-response weighting adjustment can help reduce bias, but may increase the variance. So striking the right balance between bias and variance is pretty crucial. We need to consider the trade-off for reducing bias by adjusting weights and keeping the variance within the acceptable limits. And as I said, WestEd has developed evaluation product in SAS to take these into consideration, and our package, this West Weight package, will accommodate all the fine features into the functionalities where I will introduce in the next few slides. So here is the overall architecture of the West Weight package. using the survey weight, survey design object as the data input. The package provides some main functions for doing the weighting adjustment, along with a set of nice features and functionalities for doing the diagnostic and evaluation. Finally, we will also provide a set of helpful documentation connected to statistical details as the resource for the users. And here are some uniques that I want to bring out from this R tool. It has the ability to adjust both full and replicate weights, so account for the survey replicate design as well. It has the customizable user-defined fields and will generate formatted outputs. And it has the weighting diagnostic to balance the trade-off between bias and variance through reporting the adjustment factor and sample size, with the functionality to collapse weighting cells for users to collapse weighting cells. And it also has the capacity capacity for trimming in conjunction with the raking through an iterative algorithm. So let's step into some details. This R package provides methods for doing the weighting adjustment through these couple of main functions. So this adjust weight function to do the weighting class ratio adjustment. If you remember in the previous slides introduction, it redistributes weights of non-respondent to respondent within the weighting cells. And we could use rake weights function to do the raking or post stratification, which calibrate ways to align weighted sample distribution to our known population distribution. And we could use the trim weight function to trim the extreme weights and redistribute trimmed weights to control the variation due to the extreme weights. And this rake trim function is a promoted process where it combines raking and trimming in an iterative algorithm. Since raking and trim themselves both have inherent weakness, which can be mitigated by each other, we could actually consider pair them together, pair raking or post trim, and cycle run it iteratively until converged to achieve alignment with population distribution and also respects the trimming limits. So users could alter the parameter in rake trim function process to facilitate this kind of convergence. As I mentioned previously, the R package provides functionalities for doing the weighting evaluation based on the current diagnostic process that WestEd has been using. So to evaluate this kind of bias variance balance, this package provides options to set the limitation criteria. For example, set the maximum or minimum adjustment factor allowed for full sample or for the replicate for the replicates. We could use the function to identify potential issues and flag for any violated cell. And then the user could customize to do the cell collapsing and then do the weighting adjustment again. To be more specific, in the data checks, here are some standardized outputs that will be generated in the printouts. So for each given weighting cell, we would be able to it'll report the cell size, the weighted sum before and after the adjustment, and the control totals. And it will report the adjustment factor within the cell if applicable, and it will report the flag indicator, which is 1 or 0, to identify potential concerns based on the user-defined criteria. And we also have the helper function to get the weights summary through, for example, this get weight summary function. So let's take a look at some example printouts. If we want, we're using this adjust weight function to do the non-response adjustment. Suppose we want to do the non-response adjustment to redistribute weights from this non-respondent, this NR non-respondent, to this R respondent group. During this function run, we will have first the overall description presents how the weights are assigned in general. here it says we have 50 replicates in the survey design. There are 14 cases where the weights will be set to 0. Those are the non-respondent cases. And there are 112 cases where the weights will be inflated. Those are actually respondent case. Those are actually the respondents. And the weighting cell domain, this weighting cell domain shows the definition of the weighting cell composition, just how we form the weighting cells.
2 minutes.
Okay, thank you. We also have the criteria report for how we set the adjustment limits. In this example, we said the largest factor allowed for the full sample is, like this one is 2, and larger factor allowed for the replicate is 3. And then smallest cell size allowed for full sample is 30, and for the replicate is 32. So those are our user-defined flagging criteria. And we'll have this detailed report showing the weighting summary. Actually, this is non-response adjustment by each weighting cell and kind of a cell flagging. So you see this 0 or 1, those are the cell flagging indicator. So refer to this criteria above, cells 1, 3, 4, 5, 6 are flagged since the sample size of the respondents in these cells are smaller than 30. So we could consider collapsing cells 1 and 3, and then collapse cells 4 through 6. You see this flag maximum factor is not a flag, it doesn't have 1 indicated because all the adjusted factor are within the 2, are smaller than 2. So then we could use this collapse cell function to customize the cell collapsing, and then run the adjust weight function with collapse option is collapse parameter is true again. And here is the report printouts after the non-response adjustment using the collapsed cells. You could see that there is no cell being flagged anymore. And we have the combined collapsed cell domain reported here. So this is just a quick example highlight here, showing some nice features we provide in this package. And I listed the current usage of some main functions in the appendix slide. Now that the development is on the way, new function and algorithm might be added to this R package under the expertise brought by OSDAT statisticians and programmers. Before releasing this package, we will use more data from a wider range of survey for testing this package, and our expected release date is tentatively set to September 2020, September this year. But feel free to check the slides later if you're interested, and check back for this package on CRAN later this year. Here are some reference related to our work, and then there's the appendix for you to check. Thank you for joining this talk. Any question, comments will be much appreciated, and you can also reach us through the email. Thank you.
Wonderful. Thank you so much. We have about 20 minutes for questions and answers. I'm looking in, I don't see any new ones in the Q&A. I invite the other panelists and speakers, since you can't you can't enter the questions in, you can jump in and ask questions too, and I'll monitor the Q&A. If not, I have a couple questions I can ask as well. So let me open it up to anyone who's on the panel if you have questions for the other speakers. Okay, I'm going to pose a couple questions, and folks, just keep your eyes out for any questions coming in Q&A. So Michelle, I have a question for you.
Okay.
It sounded like you all had to add some functionality that wasn't in the mice package, and I was curious if you reached out to the mice folks and shared and see if you could kind of like get a feature update or share your experiences.
I haven't reached out to the mice people quite yet. This project is still in development. but that's a good idea to reach out to the mice people. It's a part of imputation where it's not where it's a little bit different than chained equations. So it's kind of part of mice ads as well. So yeah, but that's a good idea. I should reach out to them and see if they're interested in some of the functionality. Thank you.
Yeah, thank you for a great talk. I don't know if it's the afternoon or people are just feeling less chatty. So please send your questions in. Let's see what else I have. For 6, I was curious about, you might have mentioned this, and I'm sorry if I missed it, about the sensitivity. You have a sense of sensitivity to the different activation functions and the different number of layers, and just like how to, there's so many options with deep neural networks. Did you find it challenging to kind of pick what settings to use, what functions to use?
For this research, we focus on ReLU because, as mentioned, ReLU is very computationally stable and also has a very good theoretical properties we can use to prove the consistency and the symptotic results. But we have written another paper which we compare the different activation functions, including ReLU and SeLU. And what we found is that it's a little bit sensitive, but does not change too much in our simulation results. But there's some difference for different scenarios we need to consider. But we haven't investigated the best method to choose the best activation function. I think that can be a very good future research topic to choose the optimal activation function in practice. And for other parameters like number of layers and number of nodes, we investigated different options. Like number of layers, we investigated 3, 4, and 5, and 6, and we found the results are very similar. And for the number of nodes, we investigated 50, 100, 150, and 200s, and results are also very similar.
Great. Thank you.
No problem.
Let's see, I'm monitoring the chat. Question for you, Andrew. You're gonna love this one. Can you comment on the process of getting buy-in in how you work with the management team and kind of the interest groups and other opportunities within your agencies, and kind of how that has kind of built? I know it's a little bit of inside baseball here, but can you give some insights into kind of the momentum that you've all been generating over the years? Did you hear me? Are you on mute? Let's see. I'm not hearing from Andrew, so maybe he's had to step out. Looks like he might come back. Okay, I'm seeing in the chat. Great, he's trying to sign back in. Some comments for Angela and on the previous raking macros and SAS macros. I did have a related question as well, in terms of what's driving the speed increase? Is it just efficiencies in R? Are you able to, different data types like sparse matrices or things like that? What's the intuition of why it would be faster than say SAS?
Yeah, great question. So when we were using a large scale survey data, the survey of doctor recipients, to do, when we were testing the rake train function when doing the raking and train. That's kind of an iterative process, proportional fitting process. It took us, using a SAS macro, it took us about like hours to run. And then it turns out that in R, after developing in R, it's only like it has much more like better efficiency using a parallel computing this process. So.
Okay, thank you. Yeah, I have some experience, going from say IML, custom something in SAS to R, and sometimes, you can use like sparse data types and things like that. But you're saying you're able to use parallel computing. Great. Okay. Not seeing any more questions here. I'm trying to follow the chat. Want to open it up again to the panelists to ask each other questions. We do have some time, so I'll also defer to the organizers if we need to take a break or not. But we do have some time for questions.
Oh, and I saw that
Mhm.
in the chat there is some conversation about that the macro documentation. So I had that in the reference page. If they could check the shared slide later. And Min-san shared the preceding paper, which Lou Rizzo posted in that link in the chat. So you could that is actually the reference for the West directory macro.
Excellent, thank you.